right. You want? All right, so our next talk of the day is Sudan, also talking about screening and sketching, which is a surprise for him. So anyway, take it away.
Okay, great. Thanks, Ranit. So it looks like the audio is loud and audible. So this is going to be based on some joint work with Chining Chow, Santoshini Veluswamy, who are both graduate students at MIT. Santoshini is right here. There she is, waving in the back. Noah Singer, who's an undergraduate at MIT, at Harvard, who is on his way to CMU now, Amaya Velinker, and Sasha Golevnev. Okay. All right, so very quickly what this talk is going to be about. So some part of this talk is, what CSPs are and approximation and screaming and sketching, what all of these are. I'll tell you a little bit about our results and some proof ideas. And as I've given this version of the talk many times before, each time I make a few changes. So for those of you who've been watching these slides before, you can try to detect the changes. All right, so what are constraint satisfaction problems? So the first thing that I want to stress is I'm not looking at the complexity of any single optimization problem. This is an infinite class of optimization problems. A single problem in this class is described by a family of predicates. That family of predicates is itself given by two integers, q and k. Q is going to be the alphabet size. I'm going to be looking at a set of variables, each one of which can take a value in 1 through q. Constraints are going to operate on k of these functions and k of these variables. And that constraint is some arbitrary function which tells you when it's satisfied and when some assignment satisfies it and when it does not get satisfied. And any template of functions describes one constraint satisfaction problem, an instance of this constraint satisfaction problem, and there are infinitely many instances. I think of q and k as constants, which makes for any given q and k, the size of the family is also a constant. And now you have some n variables, some very large number of variables, m constraints, again, very large number of constraints. And a constraint of over here picks one of the functions from this family that's available to you and some sequence of k distinct variables. Distinct is makes our problems more richer, but for those of you who know what this means, what the distinction between distinct and non-distinct is and its relevance to CSPs, will know that this is actually very strong, makes CSPs only stronger. So you get to pick k distinct variables, apply your constraint to them, and you do this m times. So pick a function, pick a sequence of k distinct variables, apply a function to this set, that's constraint number 1. And repeat this, constraint number 2, and so on. You get m constraints. And the question that we are asking is find the maximum, ratio of constraints that can be satisfied this way. So given a particular instance, variables and constraints, what is the assignment which will satisfy the maximum fraction of constraints? We will not be asking the question, what is the assignment, but just what is the maximum value that you can obtain? And later we'll talk about approximating this value also. Some very familiar problems that sit in this space are the maximum cut problem, the maximum directed cut problem. All of these can be expressed with q and k both being 2. You want to, in the maximum cut problem, for instance, assign variables to 0s and 1s. Constraints come along saying these two variables should not have the value 0, 0 or 1, 1. So they should have the value 0, 1 or 1, 0. And maximize the number of constraints that you can satisfy. That's the same as being given a graph and saying partition into 2 pieces so that the maximum number of edges crosses the cut. Similarly, you can model the directed cut problem, and there's a host of other satisfiability, colorability, unique games. All of these are problems sitting in the space of constraint satisfaction problems. And today we will try to talk about how to solve all of these using streaming algorithms. Now, there is in the literature some results which talk about Boolean max CSPs. Now, when you think Boolean, naturally you will say, oh, probably the variables are going to be Boolean, 0s and 1s. That is true, but these results often also implicitly restrict the families that they consider in a different way. They say every constraint can be applied to literals rather than to variables. So you can apply a constraint that you have, for instance, A or B or C should be satisfied to variable A1, X1, the literal, the negation of X2 and X3. In our case, we will not allow this, which actually makes our setting richer because there exist problems that you can phrase in our model, like the cut problem, the die-cut problem are all problems that you cannot express if you are forced to use literals. But on the other hand, when you if you want to consider a problem which only involves literals, you can actually express it by using an appropriate family of functions G, maybe not the ones that you might start with. So ours is a more expressive setting, but some previous results talked about Boolean CSPs, and they only captured these results. All right, so we are talking about streaming, as Ranit pointed out. So today we will be talking about streaming algorithms, which is something everybody is probably familiar with. These are S of n space algorithms. These are algorithms that are going to try to optimize, compute the value of the maximum ratio of constraints, fraction of constraints that can be satisfied. They do not try to compute the assignment. We will be looking at space requirements, which are significantly sublinear. And so there's no chance of actually describing an assignment on n variables. So we can only come up with a number and say, there must exist some assignment which satisfies this many or something like that. Constraints come along one at a time. So it's not as if we get all the constraints associated with a single variable together. They come up in arbitrary orders. One constraint comes along, another constraint comes along, another constraint comes along. And at the end, you have to look at the integral of all of this and see what's the instance that you had. A special case that we will be talking about are what are called sketching algorithms. Now, what are sketching algorithms? These are algorithms that usually work in the setting where, what's a streaming algorithm in general? You're given some long sequence of inputs, so some constraints, sigma 1, sigma 2, and so on. At any given moment of time, you produce a state saying, my algorithm is in state S. Let's say it's a state of sigma. Then the rest of the stream comes along, tau 1, tau 2, tau 3. Obviously, we expect to be able to compute the state at this end, S prime, as a function of the state that you were in here and the sequence that you saw afterwards. That's a general streaming algorithm. Now, a sketching algorithm will say, well, actually, I won't tell you what the whole sequence was. I will just give you a sketch of this sequence also, and now just compose these two sketches and produce the sketch at the end. The state of the algorithm can be somehow, you give me two different substreams. I give you the sketch of this part, the sketch of that part. The combined thing should be sketchable together. If you can do that, that's what's called a sketching algorithm. This is significantly more restrictive than streaming algorithms. On the positive side, our algorithmic results will usually give us sketching algorithms. On the negative side, our negative results will only, the full classification results that we have only apply to sketching. And for streaming, we have partial results. Okay, so any questions about what sketching algorithms are? All right, so in both cases, we are looking at limited space algorithms. The milestones that we will be looking at are polylog space, square root of n space, and sometimes we'll mention some nearly linear space algorithms. Okay, and I won't be too precise about this, but there's two distinct ways in which the communities have looked at approximation problems. Typically, when you're trying to prove propositive results, you just want to approximate the number, whatever is the value. This is a value between 0 and 1. We want to produce some number which is upper bounded by the actual number, while also lower bounded by alpha times the same number. So the larger the alpha, the better the approximation. Alpha equal to 1 is an exact algorithm, and you would like to get algorithms which will achieve as large a value of alpha as possible. In the negative results community, it's usually more traditional to consider this gamma beta distinguishability problem. Gamma is good, beta is bad. And you want to say, I give you an instance whose value is at least gamma, or its value is at most beta. I will never give you something between gamma and beta. Now tell me which of these two you are. The duality between these two problems is pretty tight. So if you can solve all gamma beta problems where gamma is at least alpha times, or beta is at most alpha times gamma, then you can really do an alpha approximation. If not, you cannot get an alpha approximation. So this is a tight statement. Funnily enough, our results actually go through the gamma beta distinguishability as the starting point, and this is where we'll get even our algorithmic results out of. Okay, but so this is the kind of problem that we'll be able to try and solve. So the general space of questions that we'll be looking at, I give you Q, I give you K, I give you a finite family of functions F, I give you gamma, I give you beta, and I say, okay, is this solvable with a small amount of space or not? So gamma, beta, F essentially describe the problem, and we will have to answer the question yes or no. And in the sketching context, we will be able to say this. That's roughly what we're going to get to. All right, so just like in Sefer's talk, let me sort of mention the two trivial algorithms. These are slightly different than his case. Recall Sefer was trying to find actual assignments or actual solutions. We are only interested in the value of a solution, so the thresholds are very different. Roughly linear space, O tilde of n space, suffice for solving all these problems near optimally. How? You take a subsample of all the constraints that's given to you. You might have n squared constraints, you might have n to the k constraints, and k is large, but you subsample about omega tilde of n of them. In fact, n over epsilon squared or something like that. And now just solve your problem on this instance, okay? How do you solve the problem on this instance? Store all of them and take exponential time, but linear space to solve this problem. That'll solve the problem. That'll usually give you, I mean, it's possible to solve this problem in linear space because you just have to enumerate all the assignments and find one which one was the best. So that'll give you a 1 minus little o of 1 approximation in O tilde of n space. So that's trivial 1. Trivial 2, okay, so everybody's probably known that, you know, if you pick a random assignment that'll satisfy, say, for example, in max cut, you pick a random assignment that'll cut half of the edges. So random assignments give us trivial approximation algorithms. Let me go for something even more trivial. If there is no instance in your input space, you know, I give you a family of functions, max cut, there is no graph that you can produce for which the value is less than a half. Okay, so take the minimum over all possible instances of the value of that instance. Recall the value of every instance is between 0 and 1, it's a fraction. Take the minimum over all possible instances. That's clearly an approximation factor you can achieve on every input that you get. So let's say rho min is the value associated with a particular family of functions. The minimum over all instances of the value of that instance. Can you ever do worse than rho min? I mean, no. I mean, you can just, you know, your algorithm which looks at every input and says, oh, rho min can be satisfied is always correct. It's a rho min approximation. This is actually a better approximation than the random because our constraints are not closed into negations and under literals. So there may be constraints which are always satisfied by assigning every variable to 1. Before I even look at the set of constraints you're giving me, I can tell you the value of the instance is 1 because I could assign all variables, however many of those there are, to the value 1, and it will satisfy all the constraints. That would be a setting where rho min is 1, and we get a 1 approximation. So this is the right generalization, and you can always do this. This is trivial, takes no space. I don't have to look at the instance. I just have to, before you even say, okay, the stream is starting, I'll tell you my output is this. Okay, so this should be 0 space really, but I'll call it 0 order of 1 space, and that's a rho min approximation. Okay. Now, the question that we are going to be basically asking is, when can you do better than trivial? It's really much more refined. For every gamma and beta, we are going to try to tell you, can you solve this problem or not? But in particular, we will answer the question, when can you do better than trivial? Okay. Now, this, by the way, should hint at something that's going to come up again. As such, this is not a value that's necessarily computable, right? I mean, I have to look at all instances, but there are infinitely many instances. For any number of variables that I choose, maybe I can do better. But some examination will suggest to you that, oh, look, I don't need to look at all possible instances and all number of variables. Some finite number of variables actually suffices. And this kind of thinking is actually very useful in this paper. Okay. All right, so before I tell you about our results, and let me just briefly say why study CSPs. I'll try to keep this relative. So it does contain problems of natural interest, and cut, DiCut, colorability, et cetera, are all problems that have been studied on their own. But another reason to study this class of problems is because this is a setting where you can expect to get a full classification of all the problems. Even though there's infinitely many problems out here, we can hope for, and in other settings we have seen results which say every problem, I know exactly what its complexity is. So that's something that's useful over here. And along the way, we will have to see, if there are some problems which are easy, we will have to see some algorithms which show that. In the setting of streaming, there's some norm approximations that work. There's some local explorations and some snapshots, roughly not very far from, but from the kind of the spirit of the things that Andrew was talking about earlier today. You can take a big graph, produce a small snapshot, and try to say, what can I learn about the big graph based on the small thing? These are things that streaming algorithms can try to do, and we do see some of this, though actually all we have seen so far, we've been able to analyze so far is these ones. We've never seen an algorithm actually that works in 2 to the square root of log n space, at least amongst the natural space of streaming algorithms. So, why is this happening? Why did we see something interesting happening at some space but not at other spaces? When you study things like CSPs, you might start to get some understanding for why this is happening. Okay. So these are some reasons to study constraint satisfaction problems. These are not maybe the most natural problems in every setting, but in every setting, they have given us some insight. So study of CSPs in the streaming and sketching setting, till 2011, we never really knew much about it. So Ronit co-organized a workshop at Bertinoro in 2011. They produced a list of open problems, one of which roughly suggested basically, let's study some CSPs, and we know absolutely nothing about them, neither positive nor negative results over there. Okay, so that's roughly how it was. I mean, Roby Krautgammer, who wrote the question, says, well, I only meant to study max cut, but let's take the spirit of his advice and study all of them. In 2015, some work that I did with Sanjeev Khanna and Michael Kapralov, and then further work culminating in a wonderful, really amazing piece of work by Kapralov and Krachun, showed us that getting anything non-trivial for max cut is impossible. So half approximation was trivial in constant space, no instances achieve less than half. 1 minus epsilon approximation is possible in O tilde of n space. And basically, there's nothing better. You cannot get a better half plus epsilon with little of n space. Okay, so this is it's an amazing result. It started over in 2015, but the final resolution happened in 2019 paper of Kapralov and Krachun. If people had left it at that point, we would have said, oh, no constraint satisfaction problem has an interesting CSP. I mean, you have all of these things. You can't really do much. And I'll try to motivate this a little bit later, but it turned out in 2017, in particular work of Guruswamy, Santoshini here, and Amaya Velinkar showed that actually DiCut has a non-trivial algorithm, and we'll talk about it a little bit later. In 2020, Chao, Golovnev, and Velusamy gave a complete classification of Boolean CSPs. Here, I'm stressing the word Boolean, with k equal to 2, q equal to 2. Okay, so, but this is a finite set of problems. And this didn't do the gamma beta version. As far as I know, it's really like for every problem, we'll give you the best alpha that's achievable in small amount of space. Roughly what the result said was, given a particular approximation factor alpha, it's either achievable with polylog n space, or it's going to take at least square root of n space to solve in streaming algorithms, for general streaming algorithms, not sketching at this stage. Roughly, our goal is to extend this, and we do. So what are our results? First, we get a dichotomy for sketching for all gamma, beta, and f. So for every gamma, every beta, every f, either this problem is solvable using polylog n space, or it requires at least square root of n space for any sketching algorithm. For a large subclass of these problems, we actually get streaming lower bounds, but I won't really dwell on that part today because explaining which subclass it is and so on, I mean, it's not the tight result. So we do get tight results for many problems in this space, but not all of them. But this particular result is complete classification. And along the way, presumably we give new algorithms for new problems. So DiCut, we know, had algorithms. In fact, Max 2-SAT also, and MaxSat was also given optimal algorithms by Chow, Golovnev, and Velusamy. We get many more problems for which, and in fact, future work, subsequent work actually showed that there are infinitely many new problems for which you can get optimal algorithms, infinitely many problems for which you get non-trivial algorithms using our framework, using the algorithm that we give, but then analyzing it. Now, what happens? So why do I sort of stress this difference between these two? What's a dichotomy result going to look like? I'm going to give you a gamma, I'm going to give you a beta, I'm going to give you a family of functions, and then I'm going to ask you the question, so is it solvable or not? Now, this family of functions may have lots and lots and lots of functions. You have to take some time to at least read all of these and then determine your answer. So there has got to be some, decidability criterion. How effectively can you decide this thing? Most results that we've seen in CSPs will say, well, if this family of functions can be expressed in a certain way, then this problem is solvable. If not, it's not solvable. Our result does not look like that. Instead, it just says, okay, here's some, constraint, some sort of a optimization problem to be solved in finite dimensions. Some function of k and q is the number of dimensions. Solve this optimization problem, and that will tell you whether the answer is yes or no. Okay, so this is a kind of a non-trivial decidability result. So when you want to actually, if I give you a concrete problem, so I give you the problem which is 3 and, all constraints are of the form the and of 3 literals, x1 and x2 bar or x3, etc. How well can you solve this problem? Well, our theorem will say something, but you have to run this optimization problem for a long time and figure out the answer. Figuring out the exact answer is not simple. If I now generalize this to k and, I have k literals and you have to take their conjunction, what should the value be? The exact value is now known, but it follows from analyzing what we say in our paper, but not from the theorems in our paper. So there's some wonderful work by Santoshni along with a host of undergraduates at Harvard that does this, including Noah Singer, but I won't be able to talk about that. Anyway, so there's at the space of square root of n space algorithms, we have very, very good understanding, at least when we restrict it to sketching, it's complete. Even when you're looking at streaming, we have significantly better understanding now than before. When we go to linear space algorithms, so notice linear was our sort of trivial upper bound, we still get pretty decent results, and I can say it's pretty decent in one of 2 ways. There's a vast subclass of constraint satisfaction problems for which we can basically say exactly what is the optimal threshold that you can get. So, and these will be problems that can either be solved with polylog n space nicely, or even linear space will not do, okay, or any sublinear space will not do. On an alternate, but this is only for an infinite subclass of problems, not all the problems. An alternate way of looking at our result is basically saying for every problem, every CSP that we've described so far, either and you give me an alpha, either alpha factor approximation is possible in polylog n space, or an alpha over q approximation is impossible alpha times q approximation is impossible in linear space. So we are approximating the approximation factor to within a factor of q for every problem. Okay. So those are the kinds of results that we have, and there's also some extensions to variants of CSPs and so on. But most of this talk is going to be focusing on that result here. Okay. Questions at this stage? All right. So some proof ideas. Let me start with the maximum cut lower bound. This is the first of these lower bounds, and this is, let's focus on the square root of n space lower bound. How does it look like? Let me first give you this is the typical flavor of a result in the space, right? I'll give you two distributions, one which is focused on value, instances of value close to, greater than gamma, another focused on distributions of value less than beta, and I'll try to claim that, these two are indistinguishable. In the case of max cut, where we say non-trivial approximation is impossible, we are forced to say the yes distribution is a graph with max cut value close to 1. In fact, in our case, it's going to be exactly 1. It's going to be a bipartite graph. So I will pick a graph with a hidden bipartition, and I'll stream its edges. Or I'll pick a graph which has no hidden bipartition, just a random graph, and I'll stream its edges. For some technical reasons, it's nicer to take a graph which is a union of matchings, and the whole stream will be composed of substreams. I'll get a matching, and then another matching, another matching, another matching. Either all of these matchings will be crossing the same cut, so it's a bipartite graph, or they'll be just random matchings. Tell me which one of these holds. So let's play this game. Here's the graph. I hope you have polylog n space or even more. So this is what a streaming algorithm sees. So don't think I'm being unfair to you. Okay, so is this bipartite, or is this a random graph? Okay. I mean, if you're like me, you'll say I have no idea, and yes, you should have no idea. In fact, if you have an idea, I can still claim the other as the answer, and our theorem claims that you shouldn't be able to computationally distinguish between these two settings. So these are really, it should be impossible, and the theorem is it is. You might just ask, how do you actually prove such a theorem? So if you do this thing of taking your graph to be a union of matchings, roughly what's going on, after a little while, maybe the streaming algorithm is learning some information. It's seen the first matching, the second matching, the third matching. Maybe it started to learn what the hidden bipartition looks like. So you can consider the problem that you get at this stage. Maybe it's learned everything about this hidden bipartite matching, but now let's switch the game on this thing, and let's now start giving it random edges, not from the hidden bipartition. Can it actually detect that the switch has happened? Well, it turns out exactly this problem has been studied in the literature. It's called the Boolean hidden matching problem, roughly. I give you, Alice gets a bipartition, Bob gets a set of edges, and either the promise is either all the edges are crossing this hidden bipartition, or they're just random edges. Can Alice tell Bob enough information about the bipartition for him to be able to distinguish the two? Okay, that's what is called roughly, this is more or less what is called the Boolean hidden matching problem. And this wonderful result of Gavinsky, Karenidis, Raz, Wolf, and who did I miss? Kempe. Gavinsky, Kempe, Karenidis, Raz, and Wolf, they show that actually this problem, the underlying problem that you look at over here, where Alice has a hidden bipartition, Bob is getting a random, either a random cut which matching which crosses the bipartition, or a random matching. These two things are indistinguishable if Alice is only allowed to send a message to Bob, which is little of square root of n bits long. Okay, so once you have this, and then you have the, our idea of putting all of these streams together, a hybrid argument tells us that omega of n space is square root of n space is necessary. So the square root of n space lower bound comes from the fact that the Boolean hidden matching requires communication of square root of n. Okay. The omega of n lower bound from capital O and Krachman is really much more intricate. You have to, so it opens up the hidden matching lower bound, and then takes one page of that proof and expands it into 35 pages or 50 pages, and then gets the thing. So it's a lot more complicated, and we are omitting it. I will not describe the Boolean hidden matching problem out of interest of time. And instead, let me go to this thing. I mean, so we played the game with max cut. I streamed a random graph by you, and I said, okay, can you tell whether this is a bipartite graph or it's a random graph? And I hope we all agreed that that's not something we can tell. Now consider a related problem. I have a graph in which almost all the edges are going from left to right, but except I've sort of permuted the vertices so that left to right is not visible. I've jumbled the vertices. So the DiCut value is almost 1, or it's a random directed graph. Okay, but still, you're seeing these edges and they're going in all kinds of random directions because the vertices are all jumbled up. Can you really tell the difference? In fact, so this result of Golovnev, Velusamy, and Velinker says that yes, you can tell the difference between these two. In fact, it's even more precise. Maybe 90% of the edges are going from left to right in some hidden partition, or under any partition, at most 80% of the edges are going from left to right. These two are actually distinguishable to a streaming algorithm, which is seeing these edges whizzing by. It's quite a remarkable thing. It's quite surprising. So let me tell you why this result holds to be true. So to get this result, we'll define a very simple quantity called the bias of a vertex. It's a number between positive, plus n and minus n in simple graphs, which says what's the in degree of a vertex minus its out degree. Okay, for each vertex, it's a thing. And I have a vector of n coordinates, which says for each vertex, what is its bias up or down. Okay, and define the bias of the graph to be this quantity. What is this quantity? I take the absolute value of the bias of each vertex. I sum them up over all the vertices, and I take half of it. Why half? So that it's a number between 0 and m. Okay. Now, you can prove, and these things don't take, they're not hard to prove. A good background in graph theory should be, would leave you, easy. It'll be fairly easy for you to prove this. The DiCut in a graph is upper bounded by m plus bias over 2. So if a graph has a lot of bias, what does it mean? Vertices either have lots of edges leaving and very few coming in, or lots of edges coming in and very few leaving. So that's a hint that, I should place a vertex with lots of vertices leaving on the left of the cut, lots of edges coming in on the right of the cut, and that should be a pretty good cut. It turns out that's really true. So the bias of a graph is actually a lower bound on the DiCut value. And in fact, this assignment that I gave you will get such a cut. But on the other hand, if the bias is not very large, then the cut value is also not very large. If all the vertices have in degree roughly equal to out degree, the maximum cut size will be at most 50% of the edges. So these two are fairly easy to prove. And once you have this, you have already a 2/5 approximation algorithm for the DiCut problem. Okay, so it's very simple, very nice, but wait, why is this an algorithm? The bias is a huge vector of n elements. I cannot store this entire bias vector. However, what I'm interested in at the end is the L1 norm of that vector. And L1 norms can be approximated very efficiently. Every constraint that comes in, every edge that comes in says, okay, add 1 to this coordinate of the bias vector, subtract 1 from that coordinate of the bias vector. I have to compute L1 norms under linear updates in the turnstile model. This is exactly more or less what I think the whole field of streaming algorithms was set up to do. So this has been done very well. In particular, Piotr, who should have been here, is here actually, gave one of the first algorithms for approximating the L1 norm of a vector, and you just apply that as a black box and you can compute the bias. So even though there is this graph, you have no idea what is the cut. You know there is a good cut, and you can figure out how, it's a pretty good approximation. Now going further along, this is 2/5 was not optimal. And what Chow, Golovnev, and Velusamy did was said, well, okay, let's take this other rounding scheme. If the bias is less than m/3, then let's round every vertex with to be on the left of the cut with probability half minus this quantity, and on the right of the cut with half plus that quantity, etc. And the bias value that you will get is, the DiCut value that you get is at least that much, m over 4 plus bias squared over 4 times m minus twice the bias. Okay, and this gives a 4 over 9th approximation. Okay, and you would say at this stage, okay, come on, what is this rounding scheme? What's this thing? Why should all of this be right? Why are we, when the biases are greater than m over 3, why is deterministic rounding right, etc.? None of this seems intuitive, but they gave a lower bound saying no algorithm achieves better of 4 over 9 approximation using little o of square root of n space. So not only is somehow this algorithm good, it's the best. And this analysis is somehow built in, into the structure of the problem. It's not something which is very special. So it's really very surprising that not only this algorithm, based on some simple notion like bias, you can start getting algorithms which are optimal, but their analysis involves some fairly strange polynomial and rational approximations, which are also somehow built into these problems. So it was very strange. And when we tried to extend it to other CSPs, you can see some obvious challenges. So for example, if I have a CSP, again on Boolean variables, with constraints of the form f of x, y, z is satisfied if x and y parity z is 1. Okay. So what should the bias be? When you say, you have a cut and this edge is leaving this vertex, it's clear that you want to say this vertex wants to be on the left of the cut. If it's entering that vertex, it's clear to say that, oh, this vertex wants to be on the right of the cut. But when I see a constraint like that, and I say, oh, I have a variable x which is appearing as the first variable, okay, is that making it wanting to be 1 or 0? How about if it's appearing here? Does that make it want to be 1 or 0? And how about here? So it's not so clear how to assign biases to different positions in this scheme. And other things that we're sort of looking challenging, if you want to go beyond L1, beyond binary variables, what should the analog of this L1 approximation be? So let me explain why L1 approximation comes up at all in CSPs. Okay, what is the L1 norm of a vector x1 to xn? Okay, it's really just the solution to this optimization problem. Maximize over all AIs in plus or minus 1. That's a Boolean domain of the linear form summation AI xi. Okay, so if you want to optimize a linear form in n variables, you would get an L1 norm approximation. CSPs are not linear forms. That's why you lose something in the approximation. Okay, but what happens when you're doing query vectors? What could you do? So at the very least, it would be nice to be able to approximate some linear forms in query variables. And for that, we were able to find the right thing. There are many other norm approximations that are available in the streaming literature, and we were able to appeal to those. And we said, okay, linear forms in n variables, even if they are not Boolean, we can use and do something with. But there's still this question of how are we going to use these tools? So this is where we were and were somewhat stuck. And then we took a step back. So I should finish in 5 minutes, is that or less? Okay, sounds good. So what we said, step back, was said, okay, let's forget sketching, let's forget biases, let's look at the following class of algorithms. These are very weird algorithms in the sense that they're not allowed to do anything, but they're given a lot of things to do with, to do that nothing with. So suppose I give this algorithm this entire matrix of n by k. What does this matrix contain? In the ith column, in the jth location, I tell you how often this variable appeared as the jth variable in the constraint. Let's pretend for simplicity there's only one constraint, one function in our space applied to k variables at a time. So I tell you exactly how often, excuse me, I tell you exactly how often each variable appears in each position. This is a lot of information. It's not clear how, excuse me, how a streaming algorithm is going to be able to compute this. But suppose I give you all of this, but that's all the information I give you about the input stream. I take away the stream from you, instead give you this matrix, and I say, okay, now solve the optimization problem. How well can you solve it? So you can ask the question, how well can this algorithm perform? And here's a completely tautological statement. If there are two instances, psi1 and psi2, one of which has value at least gamma. Oops. So one of which has value at least gamma, the other has value at most beta. But the matrix associated with these two instances is exactly the same. Then you cannot solve the gamma beta distinguishability problem by this algorithm. Okay, there's not even an algorithm, it's just some information theoretic statement. If this is the information, that's not going to be sufficient. It's a non-sufficient statistics thing. And conversely, if there are no two instances which have the same matrix, then it can be solved by this algorithm, though maybe in exponential time or whatever, infinite time. So this is the tautological statement, but it is the key to our classification result, because what we basically say is that this algorithm can actually be sketched in polylog space. And if this algorithm cannot solve a problem, then square root of n sketching algorithms will not work. So you put these two together, you get everything. And you should not be happy with this kind of a statement, because this is a statement which says, okay, look at this infinite set of instances, and I give you an algorithm and I prove a theorem saying if this algorithm works, it works. That's not really a very interesting statement. So you have to at least give me a criterion saying, okay, look, when is it in case one, when is it in case two? And there is a criterion. And in fact, this criterion is what leads, understanding why this is true leads us to both of these steps. So in the last slide, I will try to tell you a little bit about how these things work. Maybe this is not the last slide. Maybe there's one more slide. So the first insight over here is that actually instances, you don't need to look at n for arbitrarily large n. K times q variables suffice. You're looking for the worst instances of some type or the best instances of some type. That's easy to consider. In particular, if I give you one huge instance which has value at most beta, now take every permutation of the variables, still the instance has value at most beta. Take the conjunction of all of these things, the value is still at most beta. And once you've taken the conjunction of all of these things, all the complication in the instance is mapped onto the first k variables, because every set of k variables sees exactly the same distribution of constraints. So the entire instance has been sort of ported into the first k variables. So k variables should really suffice. But it's actually k times q, because for when I want to give you a hidden planted assignment which satisfies lots of constraints, then I might want to use sets of variables, and the sigma variable in the ith set will always appear in the ith position in the constraint and take the value sigma. Okay, so you put these two together, you will get k times q variables actually suffice. And once you have this thing, most of the other things work out. I'm out of time, so let me sort of skip to the end. There's not so much more to the rest of the ideas, but each one, the idea is conceptually simple, maybe technically can take a lot of work. And somewhere out there, we went from wanting to prove streaming lower bounds to only getting sketching lower bounds, which was a little unexpected for us. So some open questions in this area. One is, are there really non-trivial streaming algorithms which are not sketching algorithms? I mean, I'm sure this question has been asked in many other contexts before. In the context of CSPs, it's a very clean question, and we don't know the answer to that. Is square root of n space equal to linear space? I mean, are there problems which admit n to the 2/3 space algorithms which are somewhat better and so on? The answer to this is almost surely yes, but and Santoshini and I and others are working on this, but we don't have a theorem yet. So we seem to be close to saying yes, but there's still many other things. If the answer is yes, there is some non-trivial algorithm, then you have to classify all of this, and that is a wide open question. We have no idea about what could be done there. And we could even ask questions like, okay, omega of n lower bounds is the maximum we've been able to prove, can you actually get an omega of n log n lower bound, which is what you really need to store a random graph on n edges? Is that necessary or not? So I mean, it would be amazing to get an ultimately optimal lower bound in the space. That's great. Thank you, sir.
Are there any questions? Oh, sorry.
Hi, Madhu. I have two questions. The first one is whether this bias idea could be applied if the constraint, the CSP is like literals.
Sorry. Oh, are things any different if if variables are replaced by literals?
Yeah, especially whether the bias idea of the DiCut approach would work.
Sorry, I didn't catch that. So can you repeat this question again? Sorry, maybe in some other words.
Oh yeah, sorry. Would the bias approach for the DiCut problem work if your CSP had literals?
Right. So would the bias approach work if the CSP had literals? Great, thanks for the question. First, all our algorithms are really extensions of the bias approach. They basically look at every variable, every position that they appear in, and then try to assign a sort of a preference saying, if it's appearing in the 5th position and I have 7 possible assignment variable, the alphabet is of size 7, what's the sort of preference that I now have, additional preference I have for being value 3, and what's the additional preference for value 6, et cetera, et cetera. So, and it accumulates these kinds of preferences over all the constraints and then does some rounding based on that. Working with literals as opposed to variables, like I said, every problem on literals can be expressed as some other problem on just variables. You just have to have a richer collection of constraint functions. You pick out a constraint function which will say the 3rd variable will be negated and the 1st one will be unnegated, et cetera, et cetera. So you just work with that, and yes, our results do apply to all of those categories.
Okay, cool. And then I guess my other question was whether there are any results for lower bounds known for multipass algorithms.
Lower bounds for multipass algorithms was a question. There are lower bounds for multipass algorithms which rule out some cases of some kinds of desire things that we might want. So something better than saying very good approximations cannot be achieved with very little space is the kind that we get. There are very few that say that you cannot do anything non-trivial. There's none that say you cannot do anything non-trivial, and a very good candidate seems to be max cut. If I'm giving you 3 passes or 7 passes, can you get something non-trivial for max cut? And the answer seems to be, well, we don't know how to do anything, but we don't know how to prove anything.
Great. Thank you, Madhu.
Okay, thanks.